It's logical to look at induction now because the first type of induction problem we looked at was proving those series patterns. So it falls in nicely with the series topic. Because induction is not restricted to that. I mean, induction is an idea, it's a way of proving something. So we can still apply it to other sorts of things. Now, if you look at this logically, of course it's always going to be divisible by 3. And if you've got 3 consecutive numbers, I mean, one of those numbers must have a factor of 3. Okay? But that's not good enough for a proof. So we're going to actually prove it using induction that n times n plus 1 times n plus 2 is always divisible by 3. Same procedure, let's prove it's true for the first case. So let's let n equal 1. Now in this case we don't have a left-hand side and a right-hand side. So I'm simply saying, well, n times n plus 1 times n plus 2 is, in the first case, 1 times 2 times 3, which is 6. And yes, 6 is divisible by 3. So that's fine, it satisfies our condition. So it works for the first case. Now, I'll assume. Now how do you write that down? I mean, we've got to prove something. So the way we write this down is we say, well, k times k plus 1 times k plus 2 is going to equal 3 times something because it's divisible by 3. But that thing, p, I've called it, has to be a whole number. I mean, it's a fraction, no good. Got to go in evenly. So I specify p has to be an integer. Then I'm going to prove it for k plus 1. So now the next 3, k plus 1, k plus 2, k plus 3, is 3. Now I've got to change the integer, because if I say equals 3p, then I'd have to prove that those two things are equal, which of course they're not. So I'll call it q. So k plus 1, k plus 2, k plus 3, I want to get my assumption into there somehow. My assumption was k times k plus 1 times k plus 2. Well, I've got the k plus 1 times the k plus 2. If I expand out the k plus 3, so I'll have k lots of k plus 1, k plus 2, plus 3 lots of k plus 1, k plus 2. Well, there's my assumption, k plus 1, k plus 2. So I can substitute in, and we can now clearly see, hey look, there's a common factor of 3. So I can factorise, and I've got it 3 times something. But remember, that thing had to be an integer. We said p was an integer. We said k was an integer. So, I mean, if we look at this, if k is an integer, k plus 1 is, k plus 2 is, you multiply 2 integers together, you get an integer, and then p. So yes, p plus k plus 1, k plus 2 would end up being a whole number. So I can say it's equal to 3q. In this case, q would be p plus k plus 1, k plus 2, which does turn out to be a whole number. So that's not a problem. So hence the result's true for k plus 1, if it's also true for k, and we proved it was true for 1s, then by induction it must be true for every positive integer. Let's try another one. These ones are a bit more fun, I think. It's not immediately obvious this time that it's going to be divisible by 5. So 3 to the power of 3n plus 2 to the power of n plus 2 will turn out to be divisible by 5. So let's look at the first case. Sub in 1, I get 35, and yes, 35 is divisible. So that works. So my assumption, n equals k, so 3 to the power of 3k plus 2 to the power of k plus 2 will be 5 times something. That thing has to be a whole number, has to be an integer. So my proof, what I want to prove, if I substitute in k plus 1, that'll become 3k plus 3, and the power of 2 will become k plus 3. So I want to show that that's equal to 5 times something. All right. So how do I get my assumption in there? In this case, I need to rewrite the assumption, because it's too hard to substitute in 3 to the power of 3k plus 2 to the power of, k plus 2. To sub that in is a bit difficult. So if I rewrite the assumption to make 3 to the power of 3k the subject. So we said 3 to the power of 3k plus 2 to the power of k plus 2 was equal to 5p. Well, if I rewrite that assumption, I can say 3 to the power of 3k is equal to 5p minus 2 to the power of k plus 2. And that's how I'm going to get my assumption in there. Okay, let's expand out. Still not immediately obvious. I mean, obviously there's a factor of 5 in 135. Hang on. We've got a common factor here. We've got 2 to the power of k plus 2, 2 to the power of k plus 3 has a common factor of 2 to the power of k plus 2. So if I rewrite the 2 to the power of k plus 3, I got minus 27 lots of 2 to the power of k plus 2, plus 2 lots, well, minus 27 plus 2. So I got minus 25 lots, and 25 is divisible by 5. So I can factorise that one. And there we go, 27p minus 5 times 2 to the k plus 2. Only question we have to ask ourselves is, will that always be a whole number? And again, we've said k is an integer, so 2 to the power of a whole number will be a whole number, so that's not a problem. 27 times p, that's not a problem. So yes, that will be a whole number, not a problem. So that does equal to 5q in this case. Q is 27p minus 5 times 2 to the power of k plus 2, but that will turn out to be an integer as long as k and b are integers. All right, hence the result's true, etc., etc., etc. Now, in our exercise 6n, there's some divisibility ones.